Good morning, Dr. Neha.
Good morning, sir. Myself, Dharanpal, one of the second coordinator.
Good morning, Dr. Neha. I will just.
Neha madam is busy with some work, so I will take. So we are just waiting for 9:30,
Sure.
then we will start.
Can you see my screen?
Yeah, it's coming. Neha madam, are you there? So it's 9:30 and we are going to start. Sorry, sir, are you there?
Yes.
Yeah. So I'm going to start the today's sessions. So good morning, everyone. I welcome you all in the second day of this Atal FDP Novel Materials, Advances and Applications. Today we have 3 sessions, as you know. And for this 4th session, we have with us Dr. Saurya Gupta. Dr. Saurya is working as Assistant Professor in the Department of Material Science and Metallurgical Engineering at Hyderabad. He also served as visiting faculty at Cornell University during 2018. Dr. Saurya has obtained his PhD from Swiss Federal Institute of Technology, Lausanne, EPFL, Switzerland in 2015 in plasmonics. Later, he pursued his postdoctoral research from University of Texas, Austin at Cornell University. Dr. Saurya Gupta has received a prestigious Ramanujan Fellowship from DST in 2018 and has published nearly 25 peer-reviewed papers in international journals and conferences. His group is working on development of novel plasmonic devices and new materials having plasmonic properties. Dr. Saurya will be speaking on nanoplasmonic for material characterization and next generation optical devices. I welcome you, sir, in this FDP. It is a real pleasure to have you with us at this Atal platform. Now, handing over to you, sir. Sorry, sir, please. You can start.
Thank you very much, Dr. Dhanpal, for that nice introduction. So, today my talk, as Dr. Dhanpal mentioned, would be on nanoplasmonics and how we can use that for various kinds of material characterization, and we will partly see how this area can be used for realizing optical devices. As was mentioned, currently I am at IIT Hyderabad, and Dr. Dhampal, can you see my screen?
No, sir, not now. Now it's visible.
Yes.
But we are also not getting your video. I mean, if it's possible, you can switch on your camera. Yeah.
My lighting is bad, so can't do anything about it.
Yeah. Some light is coming from background, so.
Is this better?
A little better, sir. Actually, because of the background, some light is coming, so your picture is coming a little bit dark. Now it's much better, sir. Much better.
Okay. So the talk, as I mentioned, basically I will be talking about different aspects of plasmonics and how it can be used for material characterization. So the outline of my talk, first I will have a brief overview of what is plasmonics and why is it interesting for us to exploit for different applications. Right. Once having done that, we will look at two different broad areas where plasmonics is used heavily. One is surface enhanced IR spectroscopy, and in that particular area, we will look at how we can do different kinds of biosensing applications. So basically, to detect different kinds of biological molecules of our interest, right, using these structures. And secondly, how we can basically think of coupling kind of an endoscope with some kind of chemical signature method using these techniques. And finally, the second part of my talk will be based on surface enhanced Raman scattering, and which again involves the exploitation of plasmon resonances and basically uses the enhanced fields because of that. Right. So let's dive into it. So what is plasmonics? So plasmonics is basically an area of material science, physics, etc., which deals with the interaction of light with noble metal nanostructures. So for example, if you have some kind of metallic nanostructures of some particular materials like gold, silver, or copper, what you have is a lot of free electrons. These free electrons, when you shine light on it, can move with respect to the electric field of the light that you're applying. Right? So now, if this is the cuboid and this is the light that is coming in, which is given by the red arrow, the electrons will oscillate in this perpendicular direction along the electric field of the incident radiation. Right? As a consequence, under certain conditions, you will have resonance. What does that mean? That means that these electrons will oscillate together as a collective oscillation. And as a consequence, if you were to put a detector which is very far away, which is what we call the far field, right, we will measure the scattering, right? So this is the scattering spectrum of such kind of nanoparticles. So the horizontal axis is your wavelength, and the vertical axis is your scattering efficiency. And if you plot this, what you will see is, as a function of wavelength, you will have a peak at a certain wavelength, which is dependent on the material, the shape, the size, etc. Right? Now, if you notice what happens curiously at this resonance, if you look at the electric field close to this nanostructure, as shown here, right? So this structure is around 100 nanometers long, right? And this is around 40 nanometers wide. And if you look at the area close to this nanostructure, you have these kind of field distributions. And the color scheme is shown on the right-hand side of this image. So red means it has a high field, blue means it has a very low field, right? So if you notice around this cuboid, around the corners, we have very high fields to the order of 14, right? And if as you go away, your field actually decays to the value of 1, which corresponds to just the plane wave propagating through space, right? So this is at the essence what plasmonics does. It makes use of these nanostructures to enhance the electric field of light, which then can be used for various applications. So, having said that, what can we use plasmonics for? One of the easiest places where you can use plasmonics is for sensing. How do we do that? Let us say now we take this cuboid. Let's say we start with this cuboid being placed in water. So the refractive index of water is 1.33. Now, if we change and move this cuboid from water to glucose, or add, let's say, glucose to water, the refractive index will go up to, let's say, 1.4. Right? So what happens is your water is becoming optically more denser. Now, as a consequence, if you look at the same scattering spectrum as shown here, so the y-axis is the scattering and the x-axis is your wavelength, you will see that you will see two spectra, two peaks, which have different peak wavelengths for these two cases. And therefore, by looking at where these peak positions are coming and comparing it to a calibration curve, you are able to say what is the refractive index change, and thereby tell what is the concentration of your analyte of your aqueous. Yeah. So using this, a lot of people have studied various different kinds of sensing. It can be glucose, it can be in blood, it can be in various other media. But this is the simplest possible example of plasmonics that you can find. Now, where else can we use plasmonics? Now, as I mentioned, in today's talk, we'll talk about two particular applications. One is surface-enhanced IR absorption, and the second one is surface-enhanced Raman scattering. Now, for both of these techniques, what happens is the electric field to the power of 4 or square is what affects the process. For example, if you look at absorption, which is IR absorption, it scales as E square. So if you increase the electric field by a factor of 10, your absorption will increase by a factor of 100. Raman scattering, on the other hand, goes by a factor of 4 to the power 4. So if you increase the electric field by a factor of 10, Raman will increase by a factor of 10 to the power 4, which is quite a bit, right? And that is where the whole excitement about plasmonics is. So let's go back to that image of the electric field, which I had shown earlier, that is shown here on the left-hand side. And I mentioned you have these large, small areas of high field, right? These we call as hotspots, right? The electric field is very high in these regions. If I square this and look at the plot that is shown on the right-hand side, I see that this enhanced region is even getting more localized, which means the area is becoming smaller. So what does this mean for us? What it means is, if I put a molecule in this region, those molecules will get enhanced. However, if I put a molecule which is far away from the structure, they will not get enhanced. So as a consequence, in addition to increasing the signal of the molecules which are close by our nanostructures, I'm also reducing the amount of molecules that I require to see that signal. So I need lesser and lesser amount of analyte when we use this kind of strategies. So, as I said, this is a resonant phenomena. So we have to look at how we can tune these resonances, right? So the resonances can be tuned by multiple factors, right? So the first and easiest way of tuning it is you choose a proper material. As I mentioned, the typical materials of choice in plasmonics is gold, silver, and copper, right? The three traditional metals. And the reason why these are used as opposed to metals like iron, nickel, cobalt is because if you look at the permittivity, which is the material property that is of critical interest for us, the permittivity has an imaginary part, which corresponds to the losses in the material. So for these three materials and materials like this, the losses are very low, and that's why they support strong plasmon resonances. This is not the case with materials like iron, cobalt, and nickel, which have large parts of imaginary part of epsilon, right? So we cannot use those materials for plasmonic applications. Other materials which people are looking into now for various potentials of plasmonic applications, like high temperature applications, high pressure applications, etc., involve nitrides, various kinds of nitrides, aluminum nitride, titanium nitride, and alloys of different metals, right? So silver, copper alloys, etc. So yeah, silver, gold alloys, sorry. And more recently, people are very interested in exploiting the so-called high entropy alloys, which or as they are also known as multi-component alloys, for such plasmonic applications, right? So just a point of word about high entropy alloys or multi-component alloys. So the idea here is, as opposed to conventional alloys, where you have one principal alloying element, in multi-component alloys, you have 3 or 4 elements which have similar composition in the alloy, right? So equiatomic or near equiatomic alloys. So that is again something that people are looking into. The other way of changing the resonance is, of course, by tuning the shape, size, and morphology of these nanostructures. For example, here I have shown three different types of nanoparticles. One is a cuboid, one is like an ellipsoid, and the third one is basically a cylindrical particle. And each of these, if you look at the resonance, which is shown on the left-hand side, the horizontal axis is again the wavelength, and the vertical axis is the scattering. So what you notice is by changing the shape, we are able to tune the wavelength of this resonance, and moreover, we can also tune the width of the resonance. So just a reminder, the width of the resonance basically indicates what is the field enhancement that we have. That is what we call as quality factor of a resonance, right? So if I were to basically give an example, these are for the case of gold of different shapes. If I were to find the resonance for nickel or iron with the same shape and same size, these resonance would be completely flat. They would not show a resonance, or the resonance would be very, very broad, thereby making them useless or not so important for practical applications. Yeah. So, and the final way, of course, to tune these resonances is by assembling these individual nanoparticles or nanostructures in assemblies. It can be periodic, aperiodic, or it can be just single nanostructures with just with a couple of particles or multiple particles, depending on what application we would like to use it for. Right? Any questions? Please feel free to interrupt me if there are any questions that you may have. Okay. So, having said that, so let's directly dive into how we can use these structures for some of these IR and Raman applications. So, what do we mean by metasurface enhanced IR spectroscopy or surface enhanced IR spectroscopy? So here, for example, this is a schematic, right, of these structures that we are typically working with. So here, if you notice, this is kind of an array. So it's a periodic arrangement of these structures, which have two components. One is the straight vertical bar, and one is an L-shaped bar, right? So with a small gap in between. So these structures, when we periodically repeat them on a surface, we call them a metasurface. What does it mean? It's basically an artificial surface which has a certain desired property, right? So the origin of this started actually with the area of metamaterials, where people actually showed that you can tune the material to behave in a very abnormal manner. Typically what happens is light bends on the opposite side of the normal when it refracts. But by using these materials, you can actually make it bend on the same side of the normal. And thereby you can think of applications like invisibility, enhanced radiation, etc., and so on and so forth, right? But here we will particularly look at the case, how we can use these for different kinds of sensing. So now this is the typical structure. As I mentioned, the typical dimensions are in the range of a few microns, right? So anywhere between a micron to 3 microns. Now, when we shine light on this structure from the top and look at the reflected radiation, the reflectivity looks somewhat like the plot shown on the right hand side. So the y-axis is the reflectivity, which is given by R, and the horizontal axis is basically the wave number, which is the inverse of the wavelength, right? And what this spectrum shows is basically a big broad peak, which is shown at this particular point around 2000 centimeter inverse, and a couple of dips, right? So one at around 1450 and the second one around 1650. This peak at 1650 is because this simulation was done in water, and water has a high absorption in the IR in that range. But however, if you look at just the broad peak and the dip, this corresponds to our plasmonic resonances. And how do we know they are resonances? You basically look at the field close to these structures, and that is what we are doing here, right? So the red dot corresponds to this field distribution here, and the green dot corresponds to the field distribution shown here. So what we notice is around these structures, we have these enhanced fields, as in the previous example that we saw. Now, if you notice, for these two resonances, there are two different resonances, and we say that because the field distributions are different. For example, for the red one, it's mainly this vertical bar that gets the high field, exhibits the high field distribution. However, for the green resonance, you see it across the whole structure, right? So this is an example of how you can tune, you can add multiple different elements, like in this case, the bar and the L-shaped structure, to make a complex resonance of that is desired for a particular application. So now, as this is a resonant phenomena, what happens if you go away from the resonance? Let's say the green one, if you change the wave number either lower or higher, the electric field intensity actually reduces. So as a consequence, if you actually want to use it for various applications, you can think of basically making structures of different dimensions so that you can tune your resonance, right? So as I mentioned, by changing the size, you are able to tune the resonance. And if you increase the size, the resonance actually goes to a higher wavelength, right? Which means a lower wave number. So how deep do we probe? So basically this was in the XY plane, this plot. So we also are interested in the Z direction to see what is the materials that how deep are we probing in the materials that we'll get in contact with. So in that particular case, we again do a simulation, but now in the Z direction. So this is the plane of the structures. And the Z direction, what we see is this enhanced field only goes to a distance of around 60 to 100 nanometers, right? And if we compare it to a typical human cell, which is what we were interested in studying when we did this study, is basically around a few microns. So what that means is we are not measuring the whole cell for various analysis, but we are only measuring a small part of it, right? Especially close to the cell membrane. So having said that, now the basic question comes, so fine, we can enhance the fields, but why do we want to enhance the fields in the mid-IR? Why not any other spectral region? As we all know that, look, the mid-IR has these fingerprint vibrational bands, which can be used for various identification purposes, right? And the standard technique that we use is called as FTIR, right? So FTIR is basically a Fourier transform infrared spectroscopy. So just a second. So in FTIR, we use the Fourier transform of the what we call the interferogram to get the IR spectrum, right? And the IR spectrum, as we know, gives the different vibrational bands corresponding to the different bonds and the modes that we have in the molecules. For example, if you have an amide, CONH2, it can vibrate and oscillate in different manners, leading to the resonance at different wave numbers or frequencies, right? And typically, different groups have different ranges in which these vibrations appear. And as a consequence, the IR spectrum can be used to back calculate the structure or identify which molecules or which bonds are present in a molecule, right? However, a typical issue that we have with IR is the signals are very, very weak, right? So what we have to do typically, and what we do typically for FTIR, is we start with a sample which is very thick, right, to increase the signal. So the issue is, when you reduce the concentration of the molecules, or when you reduce the thickness of the sample, your signal becomes progressively weaker, right? And beyond a certain level, you cannot detect the signal from FTIR using standard means. And therefore, you use techniques like ATR, which is attenuated total internal reflection, and some question. Sorry. As the width of the resonance curve increases, what happens to the quality factor? As you increase the width of the resonance, the quality factor actually goes down. So it's inversely proportional. So the narrower the resonance, the higher the quality factor. Yes, I'm not able to see all the people, so you might have to speak up.
Yes, sir. What happened?
No. Someone had raised their hand or something.
No, I think some participants are being left out, so
Okay. Fine.
that message is coming. You can continue, sir. We can take the questions at the last, even in the chat box.
Okay. Fine.
I will read it out.
Fine. Okay. So coming back to this, so that there is because the IR signals are weak, we have to use different techniques, right? Like ATR. However, now in ATR, still you have the issue of sample volume and the minimum amount of what you call the minimum concentration that you need for detecting these molecules. So that is where these plasmonic structures are very useful, because if you remember, the IR absorption scales as E square, right? So we can reduce the concentration, still get very high signals, right? And that is the reason why we have these techniques being developed. So what do we do? So if you notice this bands that we have for different groups, for most of the biological molecules, these bands basically come between around 900 centimeter inverse to around 25 or 2600 centimeter inverse, right? So that is the range that we are interested in, and we tune our resonance in that particular range. And how do we do that? We basically scale the structure. So let's say we have the structure of a certain dimension. If we just take all the dimensions and scale it to a certain factor, all the dimensions increase, and thereby we can tune our resonance. So this is a typical example. So here, this is the wave number, and this is the reflectivity, which is normalized to 1. And what we notice is, as we go from a smaller structure to a larger structure, the resonance actually goes to a lower wave number, which means to a higher wavelength, right? Remember, wave number is inversely proportional to the wavelength. So using this means we are basically able to tune how our resonance is basically where the resonance is located and what is the resonance profile looking like. So now when we look at the samples in the optical microscope, that is, you see an image that typically looks like this. So we call these pixels. So each of these darker squares is basically a patch of these structures that we have made using electron beam lithography. So just a quick introduction to electron beam lithography. EBL, or electron beam lithography, is a nanofabrication process where we use an electron beam, like in an SEM, to write a pattern in a electron beam sensitive resist. And then we do certain post-processing to get these nanostructures. And these particular structures that we are using in our study are made up of gold, and they have a thickness of around 40 nanometers, right? So having said that, so let's see how we can use these materials and these devices for different kind of sensing. So to start with, we started with the simple case of detecting the difference between ethanol, water, and acetone, which is a very simple case that any sensor should be able to do, right? So here what we are doing is we are making a small flow cell, but for the time being, we are not flowing any liquid, we are just keeping it static. And the substrate is for this particular study is calcium fluoride, CaF2, which is basically an IR transparent substrate. So this is one fundamental difference that we have, or we will see when we go to Raman scattering, where the substrates are typically silica or glass. Right? Silica or glass cannot be used for IR-based applications because SiO2 or their derived glasses have a large absorption in the mid-IR, right, around 7 microns. Okay. So for that reason, we have to use calcium fluoride or magnesium fluoride or some sort of non-silicate based glass. So here we are measuring again the reflected signal from, we come from the top and look at the reflected signal, and the metasurface is directly inside the chamber, right? Now, when we flow different liquids, when we put different liquids here, we see the reflectivity looks very, very different. That is shown on the right-hand side. The y-axis is your reflectivity, and the x-axis is your wave number, right? And you start seeing that as you change the medium from PBS, which is phosphate buffer saline, which is water, pure water plus some salts, and to acetone and ethanol, we see that, look, for acetone, you have this red spectrum, which shows the sharp bands. For ethanol, you have these two small features close to 1100. And for water, you have this broad feature around 1650, right? So clearly, by looking at this spectrum, we are able to tell whether it's acetone, ethanol, or water. But this is a very coarse measurement where we have just changed the complete medium itself. Now the question comes is, can we do this dynamically, right? And can we detect small amounts of one, what you call solvent in another? Let's say in this particular case, we are looking at the mixture of ethanol and PBS, or ethanol and water, right? So what we do is we start with the chamber being filled with PBS, which is phosphate buffer saline, and then after a certain time, we inject ethanol. And then we keep monitoring the spectrum from the beginning till the end and see if we notice any changes in the spectrum using this technique. So What we see is this is the data that is shown on the left hand side. This is experimentally measured data. So the horizontal axis is the wave number, and the vertical axis is the time, right, of measurement. And the color basically represents the change in spectrum that you have, right? So with respect to the initial spectrum that you start with, which is buffer. And what you notice is at this point, at the black line where we injected the ethanol, immediately after we start seeing some changes in the spectrum. Before that, there was negligible change. And this change, if I basically look at the spectrum and where these bands are appearing, we see there are some bands at around 1100, which corresponds to the bands of ethanol. And we see a band around 1650, which is the band corresponding to water. And if we take the vertical cuts, so at a given wave number as a function of time, that is shown here, right? So this is time, and this is the log of the reflectivity. We see after injecting ethanol at this, after this black dashed line, we see the water signal goes down and the ethanol signal goes up, right? So this clearly tells us that, look, we can also do dynamic measurements when we start flowing different kinds of chemicals, right? So just to give a broader overview, so water and ethanol are just simple, what we call solvents that we typically use in the lab. This is not limited to this. So you can think of analyzing different kinds of pharmaceutical products, different kinds of drug impurities, different kinds of basically, let's say, carcinogenic materials in lake water, for example. That's another thing we have looked at, right? So you can look at some kind of impurity in water or something to using this method to analyze and identify it. Now, having said that, what is the limit of detection or what is the sensitivity? And for that, what we did is we did a sequential flow of different amounts of ethanol that is shown here, right? So this is the time of the measurement, and the y-axis is your change in reflectivity, right? Now, if you look at the signal, even for 1% or 2%, you see a noticeable change in the signal that you observe using this reflectivity data, right? So what does that mean? That means we are even able to detect 1% of ethanol in water using this method. And I will just remind you that if you go back to this flow channel and think about the metasurface, our metasurface is only sensitive to around 60 nanometers from the surface, right? So it is not looking at what is happening in the whole chamber, but only about 60 to 100 nanometers from the surface, right? So what we are talking about is the actual analyte volume that is being interrogated or measured is very, very small, right? So that is why the other aspect that people are actually looking at is how to couple these kind of techniques with either microfluidic or actually nanofluidic flow systems to measure basically material changes or characterize materials at that particular scale. So now this was one example of how we used these structures for detecting different solvents. Now, to more of a practical example, what we were interested in was basically how we can use these structures to distinguish between cancerous and normal cells, right? And why are we interested in that? We all know that, look, I mean, cancer, if you detect it in the early stages, it's a very, the chances of prognosis and the treatment are much higher, right? As compared to when you detect them in the last stage, detect cancer in the last stage, right? And a typical number that I will tell you, this is coming from across multiple countries, is if you take lung cancer, non-small cell lung cancer, and if you look at the prognosis or let's say the survival rate after 5 years, if you detect it in stage 1, it is about 80%. 70 to 80% is typical number. However, if you detect the same cancer in stage 4, which is the final stage of cancer, you have the 5-year survival rate is around 5%. So only 5% of the patients survive after 5 years if they are detected in stage 4. Right? That is why the detection in the early stages becomes very, very crucial. Now, what are the issues that we have when we talk about early cancer detection? One, the number of cancer cells that we have is very, very small, right? Just a quick recap. The stages of cancer are decided by how far the cancer has spread from the original organ where the cancer was detected, right? So in stage 1, you have cancer in one localized region and you have very, very small tumor that is present, right? So to detect that, you basically need techniques which can work at a very, very small concentration of cells or very few cell level. Right? You cannot basically do biopsy the standard way that we typically do it. So for that was why that was what we were interested in. So what we tried to do was basically use our metasurface device to try to identify uh, the potential of this particular technique for identifying or distinguishing between normal and cancerous cells. So how did we do it in the lab? So what we did is we took two cells, both from the colon organ, and one of cancerous origin and one from normal tissue. Right. So we take these metasurfaces and we measure the reflectivity at after different steps. So first we start with the metasurface in phosphate buffered saline. We measure the response. Then we put a layer of antibody, which is anti-EGFR. So most of these cancer cells that we were looking at have an overexpression of EGFR on the surface, and that is why we can use this antibody for capturing those cancer cells. Then we deposit these cells onto this surface. So when the cells grow, when the cells are initially deposited, they look like the circular patches. So each of these blobs that you see is basically one single cell. So and the gray area that you see underneath is basically the metasurface patch. So if you look at this particular metasurface, you are around 15 to 20 cells or so on. Right. So and then finally we let the cells grow for a certain time, and once they grow, they basically spread out, and you have these spread out morphology of these cells. And finally, we basically fix the cells, which is basically freezing them in that particular state, and we measure the spectrum in all these different cases. Right. So till here, the cells are alive, and we are measuring the response in liquid, in water. So that is another thing that is advantageous in our particular method, that we are able to do measurements of different samples in water, which is unlike what you can do in traditional FTIR measurements, where you need a dry sample. So if you look at the spectrum at these different stages that is shown here, so the horizontal axis is the wave number, the vertical axis is the reflectivity. What we see is all of these cases show similar spectrum. They more or less overlap, right? And this is a typical thing that you observe in most FTIR spectra, that the changes are very small and you need to do further post-processing to actually notice any major changes between these different steps. So once we do some post-processing, it can be done in two different ways. One, either we can use either a derivative or an absorption-based method. So if you use a derivative, that shows somewhat like this. So this is the wave number, this is the derivative of the reflectivity, and we start seeing variations in the spectrum in the different cases, right, at the different stages. And however, if you do the absorbance that is shown here, the variation becomes even more prominent. For example, the fixed cells show very prominent changes as compared to the live ones, right? Which show change as compared to just the antibody, which is basically an antisymmetric S-shaped curve, right? So, and then we can see that we see features at 1100, 1260, 1360, so on and so forth, right? So, what are these coming from? These are basically coming from the different molecules that we have in the cells near our metasurface device, near our plasmonic structure. So we did this experiment, similar experiments for different cells, different runs, and what we get is something similar to this. So here, the data is basically coming from an analysis called as principal component analysis. So what it does is, let us say I give you these two spectrum, black one and the blue one, right? And we try to find the differences between these two. We are naturally inclined to basically look at where the peaks are coming and what is the height of the peaks, right? So in this process, what we are doing inadvertently or not by choice is that we are removing a lot of data that can help us identify different spectra, right? So principal component analysis basically takes all this data or takes multiple sets of data rather, and tells the differences between these two sets of data, whether they are similar or they are different, right? If they are different, then what is the percentage of difference that you have? What is the what you call the accuracy that you have of this difference that you are noticing. That is what we did. So this horizontal axis is principal component score 1, and the y-axis is principal component score 2. The red dots that we have correspond to the data that was got from the cancerous cells, and the blue dots correspond to data that was got from normal cells. Now, these 3 columns correspond to 3 different resonant metasurfaces. So they have different resonances. So we were trying to figure out whether a particular metasurface was good for this for this classification, or were all of them showing similar trends. So what we see in all the 3 cases, right, in these 3 cases that I'm showing you, is that the clustering of the normal cells and the cancerous cells are different, right? So the cancerous cells cluster here, and the normal cells cluster over here, right? So as a consequence, what we can do is, this was the first part where we did unsupervised learning. So we did not have a known data set, but having this data set, now if someone gives us a data, right, a new data from some patient or from some new sample, we'll compare that with the existing data that we have in here, and then we can, if the new data point falls in this category, we can reliably say that it's from a cancerous cell. However, if it falls in this blue ellipse, it's coming from a normal cell, right? And if it is outside either of these, we are not sure. So this method then is not reliable in that particular sense, right? So this was how we approached cancer diagnosis. But so, as I said, the main advantages being that, look, we are able to distinguish between these 2 kinds of cells. And the other major advantage is we don't need a large number of cells. We don't need a bulk tissue that is typically used for histopathological identification, right? So typically what happens is you do a biopsy and you have millions of cells, and you are basically staining them with different dyes to identify them. In this method, what we are trying to show is that, look, by just looking at the spectrum of the cell, we are able to say whether they have cancerous origin or they are of normal variety, right? So one thing that I would like to point out is, here we have mainly what we call worked on whether we are seeing a difference or not between these 2 different kinds of cells. However, what we are not currently we have not done yet is why these differences actually originate, right? It is well known that, look, cancerous cells have different molecular expression as compared to the normal cells. But which are the differences that are leading to these spectral differences, we are not sure about it. And that is something that we are looking at currently. So now the other natural question that we have is that, look, I mean, we are able to basically make these multiple devices, right? Each of these patches has a different resonance, and we have to choose the best among them. And we don't know which one is the best for a particular cell kind. That's why we typically make all of them. The other way of doing this is you basically make one single what you call metasurface or plasmonic structure, array of plasmonic structures, and somehow tune the resonance, right? So how do we make this resonance tunable? Right? One way is during fabrication you change dimensions, but after we have fabricated it, we are not able to tune that, right? So what are the possible ways of tuning? There are multiple ways of tuning these resonances. Some of them more amenable to practical application, some not. For example, you can think of heating these structures so that the shape changes, right? So that is one way of tuning the resonance. However, once you do that, that's a non-reversible change. So once the structure has been heated, you will not be able to get it back to the original what you call shape, and thereby the resonance, right? The other way is you basically put it on some kind of flexible substrate and basically stretch it. So the distance or the size of the structure changes, and that is kind of mechanical tuning of this resonance, which again might not be possible, right? So in this particular case, what we were looking at is if you can electrically tune these resonances. So for that, what we do is we take these metasurfaces, which we call passive metasurfaces, which we cannot tune, right? Here we are working with slightly different metasurfaces or designs. So here we have a long wire which is running through with the C-shaped structures, right? Now, if you look at the reflectivity of the structure that is shown here, so the horizontal axis is the wavelength, the vertical axis is the reflectivity, we see a prominent dip. And if you look at the wavelength of the dip, we will have a strong field enhancement close to the structure, which is typical of plasmonic resonances. So now, how do we tune the resonance from passive to active? What we do is we introduce a single layer of graphene. We all know that graphene is a kind of a magic material which has excellent properties across different domains. It has excellent mechanical properties, it has excellent electrical properties, it has very good optical properties, right? So what we do here is we use the electrical and optical properties to tune our plasmon resonances. Right. So what happens is if you look at graphene's band structure that is shown here, so the vertical axis is energy, and the horizontal axis is basically your k vector, your momentum vector. What we see is graphene shows a linear dispersion close to the Dirac point. So this is the Dirac point, right? Now, depending on what is the filled state of electrons that you have in graphene, you have different transitions that are allowed in graphene. For example, if this is my Fermi energy, that is EF, if I have a photon which has an energy which is less than 2 times EF, I will not have a transition because there are no electrons to transit from the valence to the conduction band, right? However, if the photon energy is basically greater than twice the Fermi energy, then the transition is allowed, right? This kind of blocking is called as polyblocking, right? So what happens is by tuning the Fermi energy, therefore, we are able to tune the absorption that graphene exhibits and the electrical properties that graphene exhibits. So that is what we intended to do. And by this method, by applying electrical gate voltage, we are able to tune the Fermi level of graphene. So the device that we are making is shown on this left-hand side. So the device consists is basically typical of a field effect transistor. So we have the wafer is basically a p-type silicon, which also acts like a gate for us. We have a silicon oxide on top, around a micron thick. We put a single layer graphene on top of this, and we make the metasurface design exactly on the graphene patch that we have designed. And then we put 2 electrodes, a drain and the source, which can be used for either measuring the properties of graphene or for applying a bias between the source and the backgate. So by applying voltage between the source and the silicon gate, we are able to control how many carriers actually remain in graphene, whether it's p-doped or n-doped, right? And thereby control what kind of absorption process happens in graphene. Using this kind of backgating, right, as this method is called, we basically can tune the Fermi energy from around 0.05 electron volts to around 0.3 electron volts, right? The initial value is not 0, but rather 0.05, because as soon as we get graphene and start processing it, you have some impurities which stick to graphene. And thereby, its Fermi energy is not exactly at 0, but rather slightly elevated, right? Yeah. So how do we tune the resonance? So we basically, as I said, apply a gate voltage. So here we are looking at, let's say, just the reflectivity from the top. If we come in and we look at the reflected light, and we measure the reflectivity for different amounts of gate voltage. So that is shown here. So in most of the work that we do both the simulation and the experiment, and they typically correspond pretty well, right? So the left-hand side basically shows the simulation. So the y-axis is your reflectivity, the x-axis is your wavelength, and this is simulated for different amounts of gate for Fermi level. So as we move the Fermi level from 0.08, that is the black curve, right, to around 0.23, that is the pink curve, we see a shift of around 200 nanometers, right? And it's a shift towards lower and lower wavelengths, right? So similarly, in the experiments, as I mentioned, the Fermi level is controlled by the voltage that we are applying. So by changing the voltage, that is Vg, that we apply, we are able to tune the resonance analogous to the experiment. Again, it shifts by around 200 nanometers. Now, what we notice is, as the shift happens, there is not much change in the width of the resonance, only the resonance position moves. So what happens is, we still retain the quality factor of the resonance, even though we are able to tune it, right? So that is the first thing. Second thing that you notice is if I keep my wavelength constant, let's say at around 7.8 microns, the intensity actually changes significantly. Right? It changes by around 20 to 30%, which is significant. So we can use this kind of intensity change for various other applications like polarization change, phase change, etc. Right? Now, that is what we actually demonstrated, and this was published in Nanoletters. So if you're interested, you can actually look at the paper for further details. So now, how fast can we tune? Right? That is one major question that everyone asks us. That look, this is fine. You have made a device, but how fast can you tune the resonance? Because that, if you can tune it, if you can tune the resonance very fast, we can basically sweep across different vibrational bands and thereby measure the absorption that is coming from various bands right? So you can think of reducing that multiple pixels that we had, multiple devices, into one single tunable device. So here what we are doing is we are doing an experiment where we did an experiment where we are applying a sinusoidal gate voltage with a certain frequency omega g, right? And then we are looking at this modulation delta R as a function of frequency, right? So here, this is a typical variation. So this is the time in one particular cycle, and this is the reflectivity. And you see that, look, as I change the time, the signal actually oscillates as the gate voltage is varied. Now, if we plot this value of delta R as a function of frequency, that is shown here. So this is delta R as a function of frequency that we are applying. We see that at least till 10 to the power 7 hertz, this device actually operates pretty well, right? So that means that you're able to operate this device at few megahertz at the minimum, right? And how do we improve it further? So this limit that we have, this response is reducing at 10 to the power 7. This happens because the device does not have enough time for the electrons to reorganize, right? So how do we naturally increase this frequency? We can think of reducing the size of the device. So currently this was around 50 by 50 microns. If you reduce it to 10 by 10, you reduce the capacitance and thereby increase the response time. To improve, you basically play with the RC time of this device, right? So this was one aspect of how you can basically make these kind of optical devices. So what I showed you was on the biosensing side, but what we have also done is these kind of devices are also very useful when you talk about, let's say, phased array detectors, phased array sensors, or phased array radiators, right? So what we can do is these devices, if you can tune the metasurface properly, you can basically direct this mid-IR radiation in different directions as per the requirement. Okay, so that was what we had done with respect to the graphene. This was one short, quick overview, right? So now let's move on to the next part of this IR-based biosensing, which is on how we can actually make kind of a chemical endoscope, right, which basically involves these plasmonic metasurfaces. So we are all familiar with endoscopes, right? So they are basically optical fibers through which we are able to see inside the body without surgical procedures, right? So the advantage being that it's less invasive as compared to a complete surgical procedure, and it gives us possibility of investigating the surgical site prior to this operation, right? It tells us if there are any complications to be taken care of or not, right? So now what we wanted to do was think of an endoscope where instead of just getting a visual image, which is what we get most of the time, if we can get also the chemical information, right? That if you see some kind of lump or an inflamed tissue, does that correspond to some kind of a normal tissue or an abnormal tissue, right? So if we can actually do that, right? How do we do that? We basically think of making an optical fiber and making the metasurface at the tip of it, right? So this is, let's say, an optical fiber. The diameter of an optical fiber is the ones that we use is around 170 microns, which is as thick as the diameter of a typical hair strand, right? A little thicker. Now, and then we want to make the metasurface on this 200 micron kind of fiber, and then use it for different kind of sensing purpose. So this is how the fiber actually looks like when we start with. So the diameter is around 150 to 200 microns. We had a couple of different varieties. And then we deposit 60 nanometer of gold and 20 nanometer of copper on this particular fiber. And then we use a technique called as focused ion beam lithography to make the pattern of our desired dimension. And this is how the fiber looks after we have fabricated. So if you see this region which has been cut out, this is basically what we have cut out using the FIB, right? And this was the same fiber that was imaged before and after this particular patterning process. And if you zoom in, we start seeing that we have made, in this particular case, long bars with a small gap in between. So each of these bars is made up of gold, right? With a small gap of around, so each bar is around a micron and the gap is around 100 or 50 to 100 nanometers, right? And the same structure is repeated through this whole patch that we have, right? Now, why do we do this? So as I mentioned, we have this 20 nanometer layer of chromium. Why do we need it, right? So this is where the engineering aspects comes in, right? So FIB, as you might know, is basically a milling process. So it's like you are taking a very fine knife and you are basically removing material from a surface, right? So if the material that you are removing is very soft, it gets removed very, very fast. And thereby you have no control over the dimensions. So here what we are doing, this is an example where we are again milling gold, which is a very soft metal, without using any kind of chromium as a protection layer. So what we see is, if we see these structures, these were supposed to be cylindrical holes. But instead of that, we are basically getting hills because the gold has been removed because of its soft nature, right? So instead of doing this, if we put the 20 nanometer chromium on top of this, we get something that looks like this, right? Where the walls are very, very flat. So just compare the left-hand image and the right-hand image. So the quality is much more improved when we use this 20 nanometer of chromium as a protection layer, as a hard mask, right? So after the fabrication has been done, we can basically etch out the chromium using a wet etch and basically have only the gold layer as our template for the plasmonic application. So here, if you notice in this SEM image, right? So here we are basically getting this brighter region is gold and the darker layer on top is basically your chromium, right? Chromium has a lower atomic number, therefore it gives a lesser contrast, right? So this is the strategy that we used for making this high quality structures on the fibers. Now, this was another design that we did. So here, the fiber is a little bigger. It's around 200 microns big. And again, we make the structures on top